I'm Anil Kumar. Welcome to my series on logarithms. In this video, we'll begin with what are logarithms. We'll actually make a connection between logarithms and exponential functions, and that will help us to understand this topic entirely. We'll also talk about properties of logarithms, and I'll give you the proof of these properties as we go along. Once we have understood the properties, we can easily convert exponential equations into logarithms, vice versa, and evaluate logarithms. We'll have a few examples for doing so. Normally, calculators are able to find logarithms to the base 10, which are called common logarithms, right? So whenever you see just log, it is to the base 10, and the natural logs are ln, which is to the base e. We'll also see their significance and how do we do some simple startup problems solution using a few examples. So let's begin with addressing what are logarithms. So I'll take this opportunity to sketch graph of exponential functions first. And from there, we know inverse of exponential function is logarithm, right? So simple as that. So exponential function graph normally will be always increasing, kind of like this. And generally, if I write this graph as y equals, let me write here, y equals to b to the power of x, right? So in that case, we know that here the domain is all real numbers, but there are some restrictions on b, and that is that b is actually greater than 0 and b is not equal to 1, right? So these are two restrictions on b. Logarithms, as I said, is basically inverse of exponential functions. So to find the inverse, we have to reflect the graph on the line which is y equals to x. So let us say this is the line which is y equals to x. If I reflect it on this particular line, now this is which is a horizontal asymptote will become the vertical asymptote. The y-intercept will become the x-intercept. So what you have here is kind of like this. So always increasing graph which you get here, and this will be your vertical asymptote, right? So this graph which you get is basically the graph of inverse of this. So when I'm writing y equals to b to the power of x, inverse is to swap x and y, right? So I could write this as x equals to b to the power of y. Do you see that part? So that is what logarithmic graph is, right? So what we learn from here is that we'll write in short, we just write log for logarithms. So log is inverse of exponential function. Is that clear? And both are functions, right? So that is the basic thing, and inverse helps you to find the values, correct? So reverse values. So that is the beauty. So if you have anything like b to the power of x, we can find the value of x using logarithms. Well, still, what I've written here is an exponential form of the equation, right? So generally, what we do here is we write this particular equation with the same base, and we write this as log, as the name of the function. Base is b, right? So b of x, and that is the value of y. So writing this inverse function as what it inverse function is, y is equals to log to the base b of x. Now this is exactly same as what I have written here, which is x equals to b to the power of y. So these two are same things, correct? Okay. Now I hope this concept is clear to you. Let's talk about some characteristics of our logarithmic functions. So directly, since it is inverse, we get many characteristics from here. Mainly, we'll talk about horizontal asymptote, right? So we'll write exponential functions here. So for an exponential function, as x approaches negative infinity, y approaches 0 from the positive side. For a logarithmic function, when x approaches 0 from the positive side, y approaches negative infinity. So it flips. Do you see that? So it just flips, and that is how this end behavior is, right? Now, for an exponential function, we have this particular point, which is always at 0, 1, right? That's the origin. So we have here the y-intercept on the exponential function will be at 1, right? So y-intercept here on the logarithmic function, it flips, and so we have an x-intercept which is at 1, 0. It makes sense. So that tells you that this is indeed a inverse of this function. Do you see that? So it's kind of reflected, and you could take a mirror image kind of like this and get to the points. Perfect. So that's how it is. So these are some critical points which you need to understand as we go along. And as far as the domain and range is concerned, as far as the, here also for b, we have same restrictions on both the sides. B value, the base has to be non-negative but cannot be 1, since 1 to the power of x is not an exponential function, it is a constant, right? So that's the problem. Okay, so that is the major property which we are looking into. As far as domain and range is concerned, for exponential function, the domain is x belongs to real numbers, and the range is that the y value belongs to real numbers, however, y is greater than 0. Here it flips. So the domain here is x belongs to real numbers, however, the x value has to be greater than 0, right? So what do you expect from inverse? Exactly what you have here, right? So this is precisely what I'm trying to say, right? So y belongs to real numbers. There is no restriction on the range of exponential functions. Do you see that part? So let's have another look at this equation, and we'll describe this. So we are writing x is equals to b to the power of y, which is exactly same as y is equal to log of base b, right? So log of base b of x, correct? Now here what you notice is that we have y is the exponent, right? So in this case, y is the exponent. So exponent is this y, correct? So that is treated as the exponent, and the base is b, and the base is this b, correct? Base is b. So more or less you can now define logarithm as the logarithm y is the exponent to which the base b must be raised to give the value x, correct? So the logarithm y is the exponent, logarithm y is the exponent to which the base b must be raised to give the value of x. Do you understand the concept? So that is how we actually define logarithms. Perfect. So I hope this concept is absolutely clear, and be more clear as we take up some simple examples. So now let's talk about some properties of logarithms, right? You can see many of them here, Just as we have properties of exponential functions, we have some properties, and then we'll also talk about rules in the following videos. So here, when we talk about properties of logarithm, there are a few common things which we'll be considering. Log will always be written as log, and the base will is normally written here. So we have log, what is the value of log to the base b of 1, right? So I'd like you to answer these questions. What should be log to the base b of 1? What should be log to the base b of 0? What could be log to the base b of b to the power of x? And there's one exponential term. We use b to the power of log to the base b of x is equal to what? So I'd like you to actually pause the video and answer these. We'll actually go through some derivations of the proof, and then once we have the proof, we'll know exactly what these values are. From the graph, you must have seen some of these values already, correct? Now let's look into them one by one, right? So when we are saying log to the base b of 1, so let's say we'll do it something like this. We have log to the base b of 1. We don't know what this is. Let it be t, correct? Now if I want to write this in exponential form, then what will I do? I'll write this as 1 equals to b to the power of t, correct? Now 1 is equal to b to the power of t. That means what? That means t has to be 0, right? So that is only possible if we have 0 here, right? So that means t is equal to 0. So in the first case, we assume that log to the base b of 1 is t, and we found that t is equal to 0. So we can fill in 0 here, right? So log to the base b of 1, for any base, log of 1 is 0. That's what we're trying to figure out. Is that clear to you, right? Now the second one, which we wrote, is not 0. That is not possible. We'll take this later. We'll take this later, right? So let me write here log to the base b of 0. Right? But first, let's look into log to the base b of b. Okay. So we got the first one. Now second one. Let's say we have log to the base b of b. We don't know what this is. Let it be t. We'll write this in exponential terms. We say b equals to b to the power of t. So that is the exponential form of logarithms, correct? Now that is possible only by comparing the exponents, right? Strictly speaking, as you can see, t is equal to 1. So we can write this as 1. Is that clear to you? So see, we are providing you with the proof. So the first one was for log to the base b of 1, and this one is for log to the base b of b. Okay, now let's take the third one, which is, so we'll adopt the same method actually. So we have log to the base b of b to the power of x, and we don't know what this is. So let this be equal to, let's say again t, right? Okay, no harm. Let this be t. So writing this in exponential form, we get b to the power of x is b to the power of t. Now, b is the same base, exponent is x and t. That means x is equal to t. So t is x for us, so we get x here. Is that clear to you? So I've done the derivation for log to the base b of b to the power of x, correct? So we get x as the result. It makes sense. Log to the base b of b is 1, right? So this is kind of a power rule, right? Now, let's consider the next two. So we've done first 3. Let us consider this one, which is b. Log is in the exponent, right? Now, we could write this as let me write this time, because this is base, we are working log to the base b of x as t, so I'll write this as b to the power of t. So the whole thing I wrote as b to the power of t. Now that means what? That means that log to the base b of x is equal to t. And that means writing it back into exponential form, x is equals to b to the power of t. So what we have done here is, if you look into these two, we first said that b to the power of something is b to the power of t, and now we are saying b to the power of t is x. That means this has to be x. Correct? So this has to be x. So we get x once again here. Do you see that part of the proof? Okay. Now let's get back to the last one, which is log to the base b of 0. Well, this is not defined. Right? So if you write this as, we'll prove this. Okay, let's prove it. We'll do a small proof for this also of 0. So we say we don't know what this is, let it be t. Then we are saying that means 0 is equals to b over t. Well, exponential functions are greater than 0, right? So that is not possible. Since exponential functions, their range is greater than 0. They're never 0, right? It's a horizontal asymptote for them. And therefore, this is not defined. So is that clear to you? So with this, we have got our 5 basic rules, right? So once again, I'll again sketch the logarithmic function graph here, just to remind you how it looks like, right? So it is kind of like this, right? So clearly, what you see here is that we have a vertical asymptote, right, which is x equals to 0, correct? We have this very critical point, which is your x-intercept, which is always at 1, right? So 1, 0. Perfect. So these are very important points. And now let me also take help of 2 other points which are very critical. And those 2 points, which we'll use in graphing later, will be that those points are inverse of your base, right? So what we learned from here, log b of b is 1, right? So if this point is b, then that point here will be 1. That is what we are trying to say. Do you see this part? So if my base is b, so log b of b is equal to 1. Do you see that part? Log b of 1 is 0. Perfect? Do you get that part? Right. And if I have b to the power of x, in that case, we'll get this as x, and this is going to help us to evaluate logarithms. So other properties we are going to see soon when we look into examples. Perfect. So let's move on and take some examples. First one here is to write exponential equations in logarithmic forms. So there are 6 examples here. All are exponential functions you're very familiar with. Now let us see, how do we write them in logarithmic form? Correct? So getting back to where we started, basically we are looking into this type of an exponential, right? So y equals to log to the base bx. Do you see that? So this is what we are going to do in the exercise. So writing exponential functions in the form of logarithms and reverse we'll do later right here, correct? So that should be a good exercise. So let's begin with the very first one. So if I take log, so base is 5 here, perfect, base is 5 here, so I could write this as log to the base 5 of x is equal to y. Does make sense to you, right? So that is how we could write this in the logarithmic form. So y is equal to log to the base 5 of x, either way. Right? Now this is 32 is 2 to the power of 5. You know that's an exponential equation. It always works. The base here is 2, right? The base here is 2. So you could write this in this form, like log to the base 2 of 32 is 5. So the y value here is 5. You get the idea, right? So 2 to the power of 5 is 32, or log to the base 2 of 32 is 5. Is that clear to you? Correct? In this case, the base is 9. So we could write this as log to the base 9 of 81 is 2. So that is the y exponent. Perfect. So likewise, you can do them all. Now, if it is 1 over 125, you can write 1 over 125, right? So which is equals to, now this time, as you know, y could have a negative or a positive. As far as range is concerned, all real numbers. Base is 5. So we'll write log to the base 5 of 1 over 125 is equal to minus 3, right? So here we have now base 10. So whenever you have base 10, you don't really have to write 10. So even if you write log with no base, it means 10 by default, right? So log of 0.01 is minus 2. Is that clear to you? Correct? This equation here, the base is 8. So we'll write log to the base 8 of 4 is equal to 2 over 3. So that exponent is the y value, right? So in all the cases, this exponent became the y value, right? So that is how we'll actually write, right? So basically, what you learned here is x equals to b to the power of y is same as y equals to log to the base b of x. So we use this particular rule, right? It's a basic definition to get the logarithmic form from the exponential equations. Clear? Now the second one is write logarithmic equations in exponential form. So we have log to the base 3 of 81 equals to 4. So it becomes 81 equals to 3 to the power of 4. Do you see that? So this 3 remains the base. 9 is the base here. So we get 1 is equals to 9 to the power of 0. Here we have 2 equals to 4 to the power of 0.5, or you can say square root, correct? So that is the exponential form. Here the base is 9, right? So what we are looking into is this particular thing is the value x. So it is cube root of 81 is equals to 9 to the power of 2 over 3. Perfect. So writing it in the reverse way. Right? So I hope you're getting the concept. So y is your exponent and this is your base, right? So the base is 2 and y is your exponent. So we get 2 to the power of minus 2 equals to 1 over 4. Clear? Now here base is 10 since it is not mentioned, right? So that is a default value. 10 is your base, right? So base, and that is your exponent, right? So you get 10 to the power of minus 2 is 1 over 100. Clear? So that is how you could write exponential form into logarithmic forms and the logarithmic forms into exponential forms. Absolutely clear? Have a good look and let's move on to the next page, which is, now let us practice how to evaluate each logarithms. Now we are going to use two methods here. One method is to write the expression in the form an exponential form, and what we mean by that is that we are going to use this strategy, log to the base b of let us say anything x as given here is equal to t. Now this could be written as, here the base is b and the exponent is t, right? So this could be written as x is equal to b to the power of t, and then we'll make x with the same base and compare the exponents to get the answer, right? So t will be our solution, and that is, we call this as our method number 1. In method number 2, what I'm going to do is use one of our properties which we learn, and that is log to the base b of b to the power of x is basically equal to x, right? So this is the second strategy. So both are excellent methods of solving such equations. You could adopt any one of them. Perfect, right? So that is the whole thing. So you have to make the same base and then exponent and then do it, right? So let me show you these methods here. So if I have log to the base 3 of 27, I could actually show you both the methods here so that it's absolutely clear, and we can adopt any one of these methods. We could write this as, let me write it here itself, log to the base 3 of 27 is 3q, right? So this is equal to 3, right? So we get this answer as 3. Do you see that? So that's so simple, right? So we get this as 3. Now, if I say that log to the base 3 of 27 is something else, let's say t, then we can also write this as 27 equals to 3 to the power of t, and 27 is 3q, right? So do you see this? So t equals to 3, and we get the same answer because all this is t. Does it make sense to you? So you could adopt any method. So for example here, I can write this as log to the base of 99. I have to make 1 with the base 99. So that is only possible if I write 99 to the power of 0, and that straight away gives you the answer as 0. Do you see the beauty of this method? Correct? So easily you could do it, right? Now if I have log to the base 9 of 27, now let us say this is equal to t. So you could change from one method to another, follow what you like and what you understand better. So if I write, I have to convert this to exponential form, and then we have 27 equals to 9 to the power of t. However, 27 is, we know, 3 to the power of 3, and 9 is 3 square, right? So 3 squared to the power of t. Now that gives you that 3 to the power of 3 is 3 to the power of 2t. Do you see that? So 2t is equal to 3. So from here, what we get is 2t is equal to 3, or t is equals to 3 by 2. And therefore, for this question, the answer is 3 by 2. Right? So what you also see here is sometimes this helps you to give you more insight to the solution, right? But this is for simpler questions. This is extremely efficient way of doing, right? So for example here, let's adopt one of these methods. Now 81 could be written as power of 3, right? So we'll write this as log to the base 3, and 81 is 3 to the power of 4. And everything is to the power of 1 over 3. So that means it is equal to log to the base 3, 3 to the power of 4 over 3. And using this particular method, we know the answer now is 4 over 3. Does it make sense to you? So that is how you could actually easily do them. So here, for example, log to the base 2, writing 8 as a power of 2 will be 2 cubed. Now this is in denominator, and therefore I write this as log to the base 2, 2 to the power of minus 3, and clearly this is equal to minus 3. So that becomes the value of this logarithm, right? Now here it is log to the base 10 to the power of 1, 2, 3, 4 with a negative sign. Now whenever we have no base given here, we call them as common logarithms, right? So these are common logarithms. So that means the base is 10. And on the calculator, when you see just log written, right? So when you see this log written, it means common logarithm. It is to the base of 10, clear? The other one is a natural log. So let me write down the other one also, which is called natural log. So I'm writing in short natural log, and this is to the base e. So, and it's written as ln, right? So So ln x is a natural log, right, to the base e, correct? So which is same as log to the base e of x. Does make sense to you? So these are two common logarithms which are always used on the calculator, every calculator with scientific types. We have this ln, and ln means natural logarithms to the base e. Some calculators do also have other base and calculation, not all, but these are commonly available on most of the calculators, right? That's the whole idea. Okay, so let's continue. What we got here is log, that means this is to the base 10. So these two bases are same, so the answer should be minus 4. Does make sense to you? So simple as that, right? So here, you could do any method, right? So let us do this with equal to t, and we'll find what t is, right? So exponentially, we write this as exponential equation. 27 is square root 3, that is the base, to the power of t, right? Now 27 is 3 cubed. And square root 3 is 3 to the power of half, right? So half, and then we have t on top of it, correct? So that really means we are looking into 3 to the power of t by 2. Now that means 3 is equals to t by 2, right? So 3 is equals to t by 2, and that gives you t as equals to, 2, and that equals to t as 3 times 2, which is 6. So in this case, the answer is equal to 6, correct? Slightly more complicated than the others, but now I hope you understand how to deal with square roots as the base, right? So this was slightly different. Well, the base has to be positive. It cannot be negative, right? Okay. Now, the next example we will use you can use any method, right? So here we could write this as a log inside function. This is base 10 to 1024. Now what is 1024? 1024 is 2 to the power of 10, right? So we get log to the base 2, and we have 2 to the power of 10 is 1024, right? So that is equal to log, which is to the base 10, and that same base of 2 exponent 10 means you get 10, and log to the base 10 of 10 is 1, and you get your answer. Do you see how we did it, right? Okay, the next example here is log to the base 3, 10, that is the base 10, and 10 already given. So this is 9 for us. So I could write this directly as log to the base 3 of 9, right? Now 9 is 3 squares. We get log to the base 3 of 3 square, and that gives you 2 as your answer. Does make sense? Now we'll show you how to also solve it using the other method, right? So let's rewrite this. So we have log to the base 3, and we are writing this as log of 10 to the power of 9, correct? So let us be equal to t. That means 3 to the power of t is equals to, now this portion is 10 to the power of 9, the base is 9. So we write 9 is equal to 3 to the power of t, and we know that is 3 square, so that implies that t is equal to 2. So you could do the other method also, writing it in the exponential form. Perfect. So I hope you get it, right? So let me show you this one again with this method. So we have all this, let's say all this is equal to t, right? When all this is equal to t, the base here is 10, right? So we get log to the base 2 of 2 to the power of 10 is equal to 10 to the power of t. Do you see that? Now, 2 and 2 is a common base, so here we get 10. So 10 equals to 10 to the power of t, so that clearly indicates that t equals to 1, and we get the same answer as we got earlier, right? So, you see that? So any method can be adopted. Both are equally efficient ways of doing it. It all depends on what appeals to you, and sometimes the question, you may get one idea, start with that and then do it. We have also introduced to you 2 other types of logarithms. The common logarithms are to the base 10, and there the base is never written, and it's written as log. Then we also have natural logs where the base is not written, base is e, and it is written as ln. So ln is a natural log, right? So with this, let's move forward and do some more practice examples. Now let us focus on the common logarithms which are base 10 and natural logarithms which are base e, right? The first one here is log of 0.001. Remember, we are writing with the base 10. Think like this. This is log of how much? 1, 2, 3. So 10 to the power of minus 3. So the answer is minus 3. Clear? Here we have log to the base 10, 10 to the power of minus 7. So the answer is minus 7. 100. So this could be written as log. 100 is 10 square, right? So 10 square times 2.5. So here the answer will be 2 times 2.5, correct? Which is equal to 5. Then we have ln e. Now ln and e are inverse of one another. Ln e will be 1. Ln e to the power of 5 will be equal to 5. Ln e to the power of pi will be equal to pi. And here we have ln e to the power of minus 3.5, which will be minus 3.5. It's so simple as that, correct? Now here, it is same as writing ln e to the power of minus 7, so it should be equal to minus 7. The last one here is log ln e. Now ln e is 1, so we get this as log of 1, and you know log of 1 is 0. So that's it. So I hope with this, the whole concept about logarithm is well understood, right? So of course you can't master with this video, but you have a good idea. So let's get back to our basics, and which is, we have seen that logarithms are inverse of exponential functions. To solve exponential functions, we can use logarithms, and to solve logarithmic equations, we can use exponential functions, right? So these are the characteristics which are mentioned on this page. We also saw some rules of logarithms, right? And fortunately, we had proof for each. With this proof, you must have understood why we get these values, correct? And why 0, log b of 0 is not defined, right? Because exponential functions do not give you 0. Their values is always greater than 0, right? And then we took a few examples of and understood how do we convert exponential into logarithms and vice versa. And we also evaluated few logarithms. Well, these were very simple cases. In the next video, we'll talk more about some complicated questions and some interesting applications. So I hope you enjoyed this journey. Feel free to write a comment, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.